So long ago, when a single scientific calculation could literally take up a researcher's entire year. This is the story of how a huge shift in computing turned all that manual labor into, well, just a few minutes.
I mean, really, just think about that. A whole year. Piles and piles of paper, endless scribbling, and one tiny little mistake could send you right back to the beginning. Now, this wasn't some thought experiment for scientists back in the early 80s. This was the actual wall they were hitting. It was a very real barrier to discovery.
And this is what that wall looked like. You're looking at a page from a 1982 paper, and you can just see how dense and complicated it is. This was the world that physical chemists were living in, and it was a daily grind against pure tedium and, of course, human error.
Which brings us to what you could really call chemistry's pen and paper nightmare. This was a time when the biggest scientific ideas were constantly running up against the simple physical limit of what a human being could actually calculate with a pen.
And to make this super clear, check out this quote from J.F. Ogilvy, the author of that paper. Just to do one part of a bigger calculation, finding the first 8 derivatives, was a full day's work. We're talking 8 hours of just careful, focused algebraic crunching.
And here's the kicker. That whole day of work, it wasn't even enough. For the kind of precision they needed to make sure their theories actually matched up with their experiments, they had to go even further. They needed 12 derivatives. Now we're talking days of work, and the chance of making a mistake that ruins everything, it just skyrockets.
So how did they break through this wall? Well, they turned to a completely new kind of computing. Not the type that just crunches numbers, but one that could actually understand the language of math itself. They needed computers that could do algebra. Most of us think of computers as just really, really fast calculators. That's numerical computing. You feed it numbers, and it spits a number back at you. Simple. But symbolic computing is a whole different beast. Think of it less like a calculator and more like an algebra expert. It doesn't just work with numbers, it works with symbols, with variables. It can rearrange things, simplify them, solve them, just like you would on a whiteboard. And to put a name on it, this is what we call computer algebra, or symbolic computation. It's basically the science of teaching a computer the rules of math. So the key takeaway here is that the computer isn't just finding a single answer, it's actually transforming the equation itself. Now, this whole revolutionary idea didn't just pop up overnight. Oh no, it had been developing for decades, powered by these amazing pioneering systems with names that, sound like they're from some sci-fi movie from the 60s. So let's take a quick look at these early pioneers. I mean, look at this. The first hint of this was all the way back in 1953. By the 1960s, things were really kicking into gear. And this led to foundational languages like Lisp coming out of MIT, and these really powerful systems like Reduce, which ended up being a huge favorite for physicists and chemists. Okay, so we've got the pen and paper nightmare on one side, and we've got this brand new tool designed to fix it on the other. So let's see what happens when you put them together. This is where the story gets really good. Let's go back to that first challenge we talked about. That absolutely mind-numbing task of calculating 12 derivatives, something that would eat up days of a scientist's precious time.
Using an early system called Formac on a 1970s mainframe computer, that multi-day job was finished in about 1 minute. 1 minute. You see, this wasn't just a bit faster, it was a fundamental change in what was even considered possible. But wait, it gets even more wild. That same 1982 paper talks about another, much bigger problem. A calculation so massive that the author estimated it would, and I'm quoting here, probably require a year of manual effort. So how long did that year of work take with the Reduce system? Just a few minutes of CPU time. Let that sink in. A year became minutes. The impossible became routine. This was the raw power of computer algebra unleashed. And look, this whole breakthrough wasn't just some cool moment in history. It literally laid the foundation for how scientists and engineers use computers right now today. What was once this super specialized tool on a giant mainframe is now an essential part of the toolkit for pretty much any scientist. So what's the legacy here? Well, symbolic computation basically gave us a new way for computers to think with abstract ideas. It automated all those tasks that were just drowning scientists, freeing them up to, actually discover stuff. It paved the way for modern software you might have even used, like Mathematica or Maple. And its journey to being something everyone could use started early with programs like MooMath showing up on the very first home microcomputers. And all of that leaves us with one final thought. The scientists of 1982 saw a problem they thought would take a year get solved in minutes. It just makes you wonder, what problems are we facing today in medicine or climate science or anywhere else that seem completely impossible but will one day be solved in a flash by the computers of the future?